Hey, so the vast majority of you have now taken the exam. I got a couple of people who are still ill, but hopefully you received the emails with the information on them about your scores. I'm sorry about the typo in the first one. And the exam booklets are out here in the hall in these literature racks for almost all of you. There are a few of them that I have that are not there, but talk to me about those if you're one of the people without them. Any questions about outside stuff, exam stuff, whatever? I will put up a problem set shortly, but I haven't done it yet. All right, well, back to the world of air and objects. And actually, I keep leaving behind one of the obvious demonstrations that I mean to do. And we can now explain this. When I showed it to you in some form or other at one point, but before we could understand it. So I could turn on an air blower and, oops. Try again. So, when done right, the point is you should see that the ball, not only does it get pushed by the airstream, but it tends to stay in the airstream. It gets sucked into it if I do it right. And you may well have seen this sort of thing at some sort of science exhibitor. So what's the physics behind that particular effect? Well, first off, the ball is experiencing pressure drag as the air flows past it. So it has a turbulent wake on the far side of it, the downstream side of it. So it's being pushed downstream by high pressure at its front, and basically there's no high pressure at the back to compensate. So it was being held aloft by pressure drag, the result of a turbulent wake beyond the ball. Any questions about that idea? The more interesting piece, basically just air resistance holding it up. And I've talked to people who have sort of been that ball, who have gone to skydiving places where you don't actually have to jump out of a plane. You just go over a strong upward blast of air, and you can hover like that ball does, approximately, because of pressure drag. Okay, why does it go into the airstream? It's because if you remember, as the air is coming up at it, there's high pressure where my right hand is. There is no high pressure back here in the turbulent wake. The wake destroys what would be high pressure in the back if it were laminar flow. But there's low pressure on the sides. Remember the old low pressures on the sides, where the air is arcing around, bending toward the ball, and consequently is being pushed inward toward the ball because the ball has low pressure at its sides. Well, if that ball is sitting symmetrically in the airstream, those balance perfectly. But if the ball drifts out of the airstream, one side doesn't have that low pressure anymore. The air isn't arcing around it the same way. The other side has uncompensated low pressure on its surface. And the ambient air out here, where there's no flow, no significant flow, at atmospheric pressure, pushes the ball into the middle of the airstream. So every time the ball tries to get out of the airstream, the low pressure on its in the airstream side allows it to be pushed back in. Is that okay? Sort of a simple but kind of cool effect. All right. And that will fall off, of course. Stay. Okay. Where I approximately was in talking about airplanes was just looking at lift, and I'll sort of remind you the story. I don't want to dwell on some of these things too long, or we'll never get through it. But when the airstream around the wing of an airplane settles down, while it's, in fact, when the plane is in flight and everything has evolved to steady state flow and its normal pattern, the airflow around a wing has a kind of striking and somewhat remarkable flow pattern. The air that was coming along horizontally off in the distance actually arcs up at the wing. Some of it passes under the wing, some of it passes over, and the portion that passes over, because it bends inward toward that surface, has a low pressure at the surface. It bends toward low pressure, and there's therefore low pressure at the surface. So the top surface of the plane has quite low pressure, much lower than the ambient atmospheric pressure. The air going under the wing bends away from the wing. It's pushed away, and therefore it's accelerating away. It's pushed away by high pressure near the surface. So the wing develops high pressure below the wing, low pressure above the wing. And there's a net difference in pressure across that wing, and it's got an upward push. That's the lift force. And so that's what's holding the plane aloft. It's not, it's got a trivial amount of buoyant force helping it, but this is by far the dominant force, is that upward lift force due to the pressure imbalance across the wing. You can also think of this effect in terms of just the simple Newtonian view, is the fact that the airstream, which came in horizontally, although you can't see it, the drawing didn't go out far enough. It's actually a calculation rather than a drawing, although if it went out far enough, it was horizontal. The air then comes up, arcs over, and when it leaves, it is forever bent downward. It never recovers. The airflow is directed downward. It's got downward momentum. It will eventually transfer that downward momentum to the ground. So that bending of the airstream is the hallmark of an upward lift force. You push the air down, it pushes you up. And so the plane's held aloft, again, by you push the air down, it pushes up. Questions about this idea? All right. The creation of that crazy airflow, just to give it 2 cents, and then I'll go past it. As the plane is moving down the runway initially, the airflow is not structured like that. The airflow is pretty symmetric. So here's a wing. A wing, when you first start it moving through the air, and it actually has a kind of a strange symmetry to it. It's not. It's sort of, if you rotated it 180 degrees, it would sort of look the same. There's a lot of symmetry to this pattern. And this pattern takes air that was coming in horizontally and leaves it horizontal. It doesn't have any net lift. So that's the behavior when the plane is first running down the runway. It doesn't have any lift. It isn't until the plane has picked up enough speed and the pilots sort of trigger a transformation by they push the back of the plane down aerodynamically. I'll talk about that in a minute. They tilt the wing and they trigger a funny thing to happen at the what's called the trailing edge of the wing. The air is running to the right, so this is the leading edge, this is the trailing edge. At the trailing edge, there's a terrible kink here where the air has to bend around a sharp, essentially a blade at the back of the wing. It has to make that sudden turn, and that's unstable. It just breaks away. When they make it have to bend too aggressively, it just peels off. So this is more detail than you ever need to know, but I'll tell it to you anyway. It peels off, and when it peels off, it leaves behind it a swirl of what's called a vortex, a little horizontal tornado that peels off the back of the wing. And once that is left, there is a different kind of flow around the wing, and the air leaves that trailing edge smoothly. And there's some name, the Cutta condition, I think it's called, associated with this smooth departure of the wind, of the air, and then you have lift. So the plane abruptly takes off, in a sense. It goes from having nothing really pulling it off the runway to big force pulling it off the runway, and up it goes. A reason to talk about this is because that vortex is real. There really is a swirling portion of air left behind, and if you were in it, you would notice it for real. It doesn't have a well-defined end. It isn't just the width of the wing and stops. It actually continues and is attached to the tips of the wings. So that vortex that was initially left on the landing on the takeoff runway has a residual piece that runs along with the wingtips, and it's called wingtip vortices. It's still swirling air. If you want to know why would there be swirling air near the wingtips of a plane, think about it. You've got high pressure below the wing, low pressure above. It's kept stably, it's nice and stable in this direction. But what about the tip of the wing? The tip of the wing has a strange situation. It's got low pressure on top, high pressure below. Ooh, the air can sneak around the tip of the wing. And it does. And it sneaks around, and it ends up with a swirl to it. So there's a swirl left behind in the air of the airplane. And you can sometimes see this. on very humid days during landing and takeoff of airplanes, you may have seen those wingtip vortices. They show up in the air as because of humidity. Droplets of water, mist forms there, and you can suddenly see them. A point of that is you don't want to fly through the wingtip vortices of a plane in front of you. And this does happen from time to time. Those vortices are pretty intense, particularly in big planes with ordinary wings like this. And if you fly into them in a small plane, the plane suddenly just tips sideways because it's just twisted like crazy by this swirling air. I was in a DC-10, which I guess, way back when, that twice flew into the wingtip vortices of a DC-10 in front of it. We hit it once, the plane goes sideways for a while, and then a minute later we hit it again. Like they didn't learn. If you fly across it like this, it's just like hitting a speed bump. I've done that too. So, wingtip vortices. This is the reason why, or a reason why, you sometimes see modern planes they don't end with a wing that just goes out. It goes up a little at the end, a wingtip, winglet. That reduces the wingtip vortices. And wingtip vortices actually carry away energy from the plane. Swirling air is energetic air. So the wingtips, the winglets, improve the energy efficiency of the plane, along with reducing the strength of those vortices. All right. Yeah. Does the vortex return on landing? Yes. When the plane lands and comes to stop and stops getting lift, the vortex, the other end of the vortex appears and is left on the landing phase. So it's a giant donut of swirling air. It's just like those smoke rings that I was blowing with the smoke ring widget, but instead of being this big, they start at the takeoff field, they travel across the country, and they end at the landing field. So it's all self-consistent. It's kind of, well, for a physicist, it's kind of cool. All right? So look for them on a really humid day when you see planes taking off and landing. You'll suddenly see those swirls coming off the wingtips. All right. What else to talk about with this? Nah, we're pretty good. Except, okay, so now I'll take on to how does a plane sort of affect its takeoff, its rise, fall, all of that. It has two ways of controlling its lift. One of them is built into the wing to an extent, just the shape of the wing determines the flow pattern to some extent. But the other thing that happens is the extent to which they tilt the wing, and that's what's called the angle of attack I told you last time. The more they tilt the wing, the more severely the air bends in going around it. The lower the low pressure on top, the higher the high pressure on the bottom, and therefore the stronger the lift becomes. So the more they tilt the wings, the more the lift. That involves tipping the plane because virtually all planes have rigidly attached wings, and you can't tilt the wing without tilting the plane. So during takeoff, when they want to ascend, they want more lift than weight. So the force up is bigger than the force down, and the plane accelerates upward. They tilt the plane nose high, not because they're trying to go, the plane doesn't go in the direction of the nose. It's dependent entirely on the lift force. As they tilt the nose of the plane high, they simply get more lift, and the upward force dominates, and they accelerate upward. If they could tilt the wings without tilting the nose, that would be fine, and they would go up. They could have the plane nose low, tilt the wings right, and they would go up. Is that okay? So they play with the angle of attack. They can also get more lift by going faster. So airspeed matters. The faster they go, the more air they encounter every second, and the more they push downward. So sort of the simplest idea of obtaining more lift, if they're traveling very fast, they encounter a lot of air, they push it down especially hard, every kilogram of air, and they get more lift. So slow-moving planes have trouble getting enough lift to support their weight. Fast-moving planes, it's relatively easy. This is why the small planes that typically travel only 150 miles an hour, give or take, or maybe even less, they have to have big wings because they really aren't going to encounter very much air because of sheer speed going forward and touching a lot as it goes by. They have to compensate by having a big wings to touch a lot of air mechanically with their reach. All right? So, yeah. can't a commercial, I'll ask you this one, why can't a commercial jetliner keep increasing its angle of attack to rise faster? So suppose it's, it's going, it's rising, I don't know, it takes a couple minutes to get to cruising altitude, 10 minutes or something like that to get to cruising altitude in a jet. Why can't they do it in 1 minute? Just get more lift, just tip the plane further and further. And what do you think is the reason why they can't do that? The first is, they'll start flying in loop-the-loops. How many think that? Nobody. Turbulence will develop behind the wings. Okay. How many think the engines won't point forward enough? How about passengers will fall to the back of the plane? It's B. It's turbulence. Okay. Why not? Okay. When the plane is flying approximately horizontally, is it tilted approximately horizontally, these wings are streamlined objects, which means that they do everything they can to maintain laminar flow on both the top and bottom surfaces. And the result is a very small wake, very small turbulent wake, and very little pressure drag. So in contrast to a ball, which it would be described as a blunt object, which does not control the airflow well, it does not maintain a beautiful laminar flow to the end. The airplane as a streamlined object does maintain laminar flow. Okay? But it's not a laminar object. It's not a streamlined object when it's flying like this. It's a blunt object. And somewhere in between this and this, there's a transition. The transition is known as, it's a stall point. It's an angle at which the airflow traveling over the wing stalls. And the stall is, we've already seen the stall, although I didn't call it that, with airflow around a ball. Remember, when the air is rushing at the ball, high pressure here, low pressure around the sides, and then as the air tries to go from the side to the back, the innermost layer stalls, it comes to a stop. It doesn't make it to the back, and it peels the airflow off the ball. The same thing can happen in a plane. That the airflow that was trying, they tilt and they tilt and they tilt. The airflow was trying to go over the top. This low pressure here at the leading edge, on the top of the leading edge, has to make it to the back of the wing, which is at higher pressure. So it has to go from low pressure to high pressure. It's going into a rising pressure. This is not fun for that air. It, in principle, has the energy to do it, but the innermost layer rubs a little, and it's potentially, it could come to a stop. And if it does, it peels the airflow off the top of the wing. And so you suddenly get a huge increase in the size of the turbulent wake, and consequently much more drag, and you lose most of the lift. So the plane abruptly goes from flying beautifully to a slowing object that isn't being lifted adequately and begins to just plummet. So that's called stalling in a plane. And here's, I forget how much I've told you. The semesters blur after a while, but I was talking about this a little cavalierly some number of years ago, and one of the students had herself lost her father to a plane stall. Small planes, this is a serious hazard, particularly for small planes, stalling. It happens often during landing and takeoff when the plane is not traveling very fast, and therefore is having trouble getting enough lift to support its weight. So the obvious solution to not having enough lift when you're in a hurry to get more lift is to tilt the plane too much, because the lift does increase for a while until the flow stalls and it peels off the top, and you very abruptly lose that lift and develop serious drag problems. So there are sensors on all, I think probably all modern planes, small or otherwise, called stall warnings, that if you tilt the wing too much and are in danger of stalling, the klaxon goes off, wah, 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 and your immediate job is to tilt down the nose of the plane, and increase speed. Hit the throttle and pull the nose down, because you do not want to lose the airflow over the top of the wing. Okay? So that's the story of stalling. Here's just an illustration of it. You tilt the wing too far, it has a limit beyond which the pattern of airflow over the top suddenly abruptly turns into a turbulent one, not a beautiful streamlined one. Okay? a little bit about wing structure. Small planes don't change the shape of their wings, but big planes do. So any of you who've flown in a commercial, even a turboprop, but so any of the commercial jets, the plane changes the shape of its wings in flight. During landing and takeoff, it extends components known as slats and flaps forward and backward out of the plane to make the wing bigger. Why? Well, because at takeoff and landing, it wants to be able to travel slowly. It doesn't want to take off or land at 600 miles an hour. It wants to obtain enough lift to support its weight, even though it's traveling at a quarter of cruise speed, or something like 150 miles an hour. It does that by enlarging its wing temporarily, and also making it more curved temporarily. And so it extends those parts. When it finally is flying and is at cruising altitude, full speed and all that stuff, or if even before it gets to cruising altitude, when it gets up to serious speed, it can pull those pieces in. It does not need to touch as much air by virtue of having big wings. It's going so fast, it's going to touch a lot of air. So it can get the lift it needs without having a big wing surface. It pulls all those pieces in. One other cool thing that they do, I leave stuff all over the place, is they have things like this vein in here that leaks a little bit of the air that was going underneath the wing and is therefore high pressure air. It leaks it through the vein area and onto the top surface of the wing, where it adds extra high energy air that's packed full of ordered energy, and helps keep the airflow attached to the surface. This is one of the tricks for controlling the air, for assisting the airflow going over the wing in its attempt to go from low pressure at the top front to high pressure at the trailing edge. That air, you don't want that air to stop, so you help it along. Shoot extra high energy air into it. Trip the boundary layer with those vortex generators that they put, the little studs that stick up from the top of the wing of many planes. Anything you can do to make sure the air continues all the way to the back end of the top surface of the wing. Okay? How does a plane turn? And a plane steering a plane is not like steering a car. If you were steering a car and you wanted it to, so if the plane steered like a car and you wanted it to turn, if I wanted to turn toward you, we would just do this, right? Never tilting it this way. None of this. Just, well, it is possible to make a plane do this, to rotate like this, but the effect is going to be the following. The plane will suddenly be flying like this, which is kind of bizarre. It's slipping sideways. Actually, you do not want to do this in a plane. It's not good for the airflow. That tends to lead to bad things. So what do? If they want to accelerate, if they want to turn toward you, that means they want to accelerate. A turn, as you recall, I hope, is an acceleration towards the inside of the turn. So the plane needs a force to turn toward you. The plane somehow needs a force this way. So where's it going to get that force? Well, it gets it from its own lift force. It uses the lift for two purposes simultaneously. It can multitask. It uses the lift force in part to support its weight, but also to make it accelerate toward the inside of the turn, and it does this by lowering the inside wing and raising the outside wing. It tips. Once it's tipped like this, the lift force, remember lift is something of a misnomer. It's any force that is at right angle to the airflow. So you can have lift up, you can have lift to the right, down, anything. Those are all lift forces. In this case, when it's flying like this, the lift force is pretty much that direction, perpendicular to the two wings. So now that force is partly upward to support the weight, and partly toward you all to cause acceleration toward you all. So a tilted plane like this accelerates to its own left. And that's, again, I hope this is something you remember feeling in an airplane. And those of you who've flown, that when they want to turn, they tilt the wing. And this is, it can be kind of startling to people who are uncomfortable. I am not a comfortable flyer, never really have been. But so when they abruptly go, sometimes you get somebody who's fresh out of the military or something like that, and forgets that they are playing chauffeur, not like adrenaline junkie. and they decide, okay, we're going to turn left. Whoa, like that. And everybody's, what was that? The left side of the plane suddenly is really low. And you're seeing the ground out of it. You can do it more gently, but that's the basic idea is you want to lower the inside wing, raise the outside wing, and then go around using the lift force to do the turn. All right? To make these various changes, what do they use? They use control surfaces, and there are three important ones, or groups. There are ailerons at the outside edges of the on the wings, the main wings, on their back surfaces. And again, if you've flown, you've watched these things moving around as they tip the plane or not, or even just to keep it level. These surfaces, their purpose is to change the lift of one wing, the left wing versus the right wing. So if they reduce the lift on the left wing and increase it on the right wing by changing that flow pattern, they can cause a torque on the plane that lowers the left wing. So they briefly do that until the wing's lowered, and now they'll turn. When they're done the turn, they briefly increase the lift on the left wing and lower it on the right wing. They return to normal. Okay? Two other control surfaces they have to work with. Suppose they want to increase their lift in order to accelerate upward. They play with the horizontal stabilizer in the back, and they adjust this. It's a small wing. Its purpose isn't to support the weight of the plane so much as to determine how the tilt of the overall plane is, and therefore the wings. So if they want to increase lift, they adjust these control surfaces back here to push down. So they get an aerodynamic lift force downward that tilts the plane so that it gets more lift out of its main wings and accelerates upward. If they want to come in for a landing, they do the reverse. All right? The last stabilizer that they've got is the rudder. And this, on the vertical, I don't even know I forget what it's called. The vertical tail piece, they can adjust the lift left and right. They can get leftward lift, rightward lift, rightward, leftward, and pivot the plane this way. And it's actually important when they lower the wing, they also want to pivot the plane like that. They don't want to just accelerate like this. Then they're flying. They're not going through the air. The air isn't coming over the wings properly anymore. So they use that to aim the plane properly to get proper airflow over its wings. And these all have names that I quickly forget. All right? So that's flying a plane approximately. Last thing to worry about is propulsion. If you just take a plane with no propulsion, so it's just a glider, it'll fly fine, but it will gradually lose forward speed or altitude or both. Why? Because it's going to experience drag forces opposite its motion through the air. And even if it gets rid of like viscous drag force, it's never going to get rid of it. It's small, but you're never going to get rid of it. The air's going past the wing. It's going to rub. Pressure drag, it's small, but not zero. You do get a little turbulence behind a plane. So it's got pressure drag, it's got viscous drag, and it's got induced drag, which I mentioned from time to time. Induced drag comes about from the very act of obtaining lift. You can't pass through motionless air, obtain lift, and not get some drag force. The drag force comes about because you have disturbed the air. You've given the air energy. It's moving now. It wasn't before. It's moving. That had to come out of something. So you had something did negative work on the plane. And that negative work is done by induced drag. The details, I mean, there they are, but we no point in going into them. So if you want to keep the plane moving at the same altitude, you have to push the plane forward. You have to do positive work on it. The plane if the plane loses altitude, then it's using its gravitational potential energy to compensate for the energy that's being sucked out of it by drag forces. But if you want to maintain constant altitude, you've got to push the plane forward. And so the pushers are propellers and jet engines. The basic idea is to use the air around the plane to push the plane forward. How do you do that? Shove the air backward. It's a lot like rocket propulsion, but in a rocket, the rocket is using material it had on board, the fuel it was launched with. An airplane has an easier job. It has to take the air near the plane and shove it backward, and then it can get more. So the mass is no longer precious. You can the plane can just keep grabbing mass that's just out there and throw it backwards, and this is good. It gets propulsion. So it doesn't have to be as miserly with mass. And it turns out the most efficient engines are ones that are the least miserly with mass. They want to grab as large a mass of air as possible and throw it back slowly. If you're going to give the air backward momentum in order to have it give you forward momentum and to make up for the momentum you're losing to drags forces, you got a choice. You can grab a little mass of passing air and throw it very fast, and you'll get in response the momentum you want. Or you can grab a great big mass of air and throw it back kind of slowly. Same momentum. So far, so good with that idea? Little mass, fast. Big mass, slow. There's a difference between those two, though. If you take a little mass and throw it fast, it carries away a huge amount of energy. Why? Because kinetic energy, depends on the square of the speed. So if you double the speed in order to get the momentum you want, you're quadrupling the energy you're giving that stuff. So if you've got a choice between throwing 1 unit of mass at 2 units of speed, or 2 units of mass at 1 unit of speed, the big mass slow speed uses half as much energy. This is useful not only in airplanes, as we'll see. This is useful in everything else, like swimming. When you're swimming, you've got two choices to propel yourself forward, because a person who's swimming is basically like a plane, propelling themselves, not with propellers, but with their hands and their feet. If you got a choice between taking a little mass of water and throwing it backward fast, or a big mass of water and throwing it back slow, opt for the big mass thrown slowly. It takes away less energy from you. And so better swimmers grab more water. This is why when you put fins on and stuff, you suddenly become a better swimmer. You get propulsion really picks up because you can grab bigger chunks of water. The more, the better. Yeah, Savannah? Yes. Does the density of the air have anything to do? As the air gets less dense with great altitude, it gets easier to move through it. The drag forces reduce. You have to compensate for, so that's good, but sort of the lift forces. You have to now move faster or have bigger wings. So at high altitude, getting lift becomes more difficult. And this is why planes ultimately can't go above a certain altitude. They can't go fast enough to hit enough air per second to support their weight. So some of the crazy planes, the U-2 spy planes and stuff like that, they were made as light as they possibly could be. I mean, basically they were worrying about 1 pound here and there to try to get the thing up to 70,000 feet or something, because the air is so thin there, it's not doing you much good deflecting it. So drag force goes down, lift goes down correspondingly. Grabbing enough mass to throw backwards also becomes tricky. So there are all kinds of problems at high altitude that show up. Yeah. What if you bring the air from the Earth's altitude up there and throw it back? Then you have a rocket plane. And the fastest planes of an era, sort of even before my time, were rocket planes. The first planes to go through the sound barrier, which isn't a barrier at all, it's just a certain speed, were rocket planes, because they couldn't make the plane go fast enough. But now they're bringing mass with them and throwing it backward, because they can't scavenge enough in their vicinity. Other questions? All right, so a propeller, a propeller plane, what it is a rotating wing. So instead of having a wing that waits for the air to come by it, just take a surface, design it like a wing, so it's nice and streamlined, all that, and sweep it deliberately through the air. Around in a circular motion is the classic way to do this. And in that case, air is rushing past the wing. It develops a high pressure side on sort of the underside, what would be the underside, and low pressure on the what would be the top, and you get lift force. And the lift force can be in whatever direction you like, depending on how you orient this spinning wing. And so what a propeller is doing is it's taking a wing. This is a slice through the propeller. There's a wing shape, aerodynamic. It's called an airfoil, and it's sweeping in this picture downward through the air, which means the air is rushing over it, sort of in an upward direction, and it develops lift, not upward, but forward. So that is the thrust force then developed by the propeller that is pushed forward by a lift force. And Orville Wright was the person who figured this out. So there's this sort of mythology that, or common thoughts that the Wrights were just two bicycle mechanics from Dayton, Ohio, who were hacking around and didn't know very much. But actually, they were among the most sophisticated aerodynamicists of their era. And Orville Wright's, I don't know him personally, Orville, revolutionized propellers, because prior to his work, and the brothers together, and they're working, they had a wind tunnel, they had go to Kitty Hawk and see the museum there. It's not very far away. Prior to their work, all the propellers were made like rotating paddles, essentially. They were chronically stalled. The airflow over the top was chronically stalled. They had turbulent wakes behind them. They were not aerodynamically designed properly. So they were suffering from pressure drag the whole time, and therefore very inefficient. So suddenly there were efficient propellers when they turned propellers into rotating wings, and along with many other things, their propeller dominated air flight for like a decade. So, rotating wing gets a nice forward push by way of lift forces. The problem with propellers, ultimately, is that they work right in the onrushing air. So as the plane goes faster and faster, their ability to get lift as they go into this roaring windstorm diminishes. All kinds of problems start to show up when the air is coming at you, say, at 600 miles an hour, and you're trying to spin something through it and obtain lift. It doesn't work well. To begin with, you need to be able to adjust the pitch of the wings, which is basically their angle of attack. So at low speeds, the angle of attack is one thing. At higher speeds, you have to tilt the leading edge of the propeller into the onrushing wind to take advantage of it. So if you've ever flown on a modern propeller plane, the wings of that propeller rotate, and they change their rotation depending on how fast the plane is going. But still, above about 200 or 300 miles an hour, propeller becomes pretty inefficient. It's basically hard to swim. It's like swimming. When you're swimming, you're grabbing the water that's going by you. It's okay if you're propelling yourself at low speeds, but suppose for some reason or other you're traveling 60 miles an hour through the water and you're trying to reach out and grab the water and throw it back. That suddenly becomes a much harder task. You might not even be able to move your hand fast enough to get any push. It might be a net loss to try to grab that water rushing by you. So the solution is to go over to a different type of propulsion, jet engine. And the details of jet engine, finally, are complicated, not very important. The main thing about the jet engine is it does not work in the open flow of air around the plane. It takes the air rushing toward the engine into a diffuser. And when the air enters that diffuser, it slows down and its pressure rises. It's using Bernoulli's stuff, right? It's turning its kinetic energy. It's traveling fast as viewed from a person on the plane, in the inertial frame of the plane. It's fast-moving air. It goes into the diffuser. It spreads out and slows down. And so the air going through the engine doesn't go through at 600 miles an hour. It goes through maybe at 200 miles an hour, which is slow enough that you can get the job done. It goes through a series of compressor structures, so that the purpose of which is to pack the air molecules more and more tightly. This does involve doing work on the air, so energy is being invested in the air by these compressors. It will be paid for later on. The compressors are actually powered by turbines at the outlet. So these compressors here are powered by turbines at the outlet of the jet engine. But the point is to get very high pressure air here in the business portion of the engine. So it's high pressure, it's high density, and that supports combustion. Even if you're at 30,000 feet, I'm not sure what a candle would look like if you lit it at 30,000 feet. I'm not sure it would burn properly at all. The air's getting pretty thin. But in the compressed air inside the jet engine, no problem. You can inject fuel and burn it. And when you inject fuel and burn it in this engine, the number of particles increases, in part because the fuel molecules break down into littler pieces. And the other thing that happens is all the particles have more thermal energy. So they're traveling faster, hitting harder. You have a lot more, you can have a lot more pressure or a lot more volume, or some mix of the two. And ultimately you end up with, in this drawing, I probably should modify this drawing. What comes in is sort of a narrow flow of gas entering the combustion chamber, exits as a much wider flow of gas. So you've got high pressure pushing on a small surface area at the front. Is that true? No, I'm messing it up. I'm trying to get a justification for why you get a net forward push out of this. Let me just leave it at the simplest. The gas ends up traveling out much faster than it entered. So the air entered at 600 miles an hour. By the time you burn fuel in here, and I'm basically going to say magic occurs. You burn fuel in, the gas that goes out at maybe 1,000 miles an hour, much faster than it went in, and it therefore carries more momentum out than was received by the air coming in. And there's a net forward push on the engine. Okay? Yeah, I have to sort of remind myself of all the reasons why this works. It's not straightforward. This is more straightforward. That engine I just showed you is what's called the turbojet engine. This is apparently no turbojet engines are used in commercial planes anymore. They were great in the 40s and 50s when they were first invented. The problem is they push too little gas and throw it out too fast. Remember I told you that's a bad idea? Don't grab a little air and throw it fast. Grab a lot of air and throw it slow. And so the turbofan engine does that. It uses the turbojet engine as a power source. It's a great engine that operates well at high altitude, whereas the engine of your automobile, which we'll talk about in a week or two, is not good above a certain altitude. The air is too thin to support its operation. And then you start needing turbochargers and stuff. So this actually a turbojet engine has a lot of the features of a turbocharger, which is a bit something for our future. So it uses that as a power source for spinning a giant fan, the turbofan. What distinguishes the fan from an ordinary propeller, though, is that fan doesn't operate in the open air. If it did, it would be called a turboprop. And there are turboprops, and they're very useful, but they're working in the open air. And they have to handle air that's going by them at the speed of the plane. The turbofan is working in the open air. It's working in the air in a duct after a diffuser. And that air has been slowed down. So the air comes in at, say, 600 miles an hour. It goes into this diffuser duct and slows down to 200 miles an hour. The fan now can leisurely do work on it. It's using lift effects to do this. It does work on that passing air and speeds it up. And that air, it certainly puts energy in it, increases its total energy. And so that air then goes out a nozzle at the end, and in going out the nozzle, it turns all of its energies into kinetic energy, and it goes out faster than it arrived. So there's a net push backward on that air flying around the duct. Nothing's being burned in it. It's not part of the combustion process. It's just air that was slowed down temporarily. It was pushed backward by the fan and given energy and now it's leaving through a nozzle. And so turbofan engines work with much more air, and they obey this concept of push as much air as you possibly can, but do it at low speed. You get more efficient propulsion. And so you've seen turbofan engines on many planes, particularly some of the jumbo jets have turbofan engines that are huge. Two people could stand in these things top to bottom, because they're giant diffusers, taking the air, rushing in, having it slow down, pushing it backwards, then shooting it out a nozzle at high speed. Okay? So that's airplanes. Since I've got it here, I don't want to leave some of this stuff forever. I'm going to do, the next topic is wood stoves. I mean, rather than put it up there, I just show you some of the story behind wood stoves. Wood stoves are going to be about heating a room and having heat flow from the wood stove, which is going to be the hottest thing in the room, to the rest of the room, which is colder. And it turns out there's a second way of transferring energy from one object to another. We've already seen that energy flows as work from one object to another. That's the mechanical means for transferring energy from something to another thing. I can transfer energy to these tongs by doing work on them. I exert a force on them, and they move a distance in the direction of my force. I did work on them. That's energy transfer. The second type of energy transfer is the thermal way of transferring energy. It's when energy flows as what's known as heat, from a hot object to a cold object. So energy flowing mechanically from one object to another is known as work. When it flows thermally, it's known as heat. So the purists, heat, you don't have heat. You don't hold heat any more than you hold work. Work is energy on the move mechanically, and heat is energy on the move thermally. Do I care about the purism? No. But I'll tell you anyhow. So rather than make heat flow from something that's very hot to the rest of the room, which is kind of boring, we can make heat flow from the room, which is very hot, compared to liquid nitrogen, because my usual rule, any excuse for liquid nitrogen is a good excuse. So this now is the coldest thing in the room, and everything in this room is trying to transfer heat to it. So heat is flowing from hot objects to cold objects. As we'll see, two objects that are at the same temperature do not exchange heat. That's the whole idea of what it means to be at the same temperature. Temperature actually orders the exchange of heat. So that anything that's a little higher in temperature than another thing will transfer heat from the higher temperature one to the colder one. It defines what temperature means. So this is the coldest temperature in the room. Therefore, everything here will want to transfer heat to it. And different things do different, So I was going to bring flowers in, but I thought, why buy flowers when I can simply cut weeds out? So locust is a weed in my garden. And so if I transfer heat from locust, glass locust, I froze it to the point where it's so rigid it just shatters. You can pound bananas. You can freeze a banana to the point where it can be used as a hammer. I didn't bring nails in. Usually the banana shatters before the nail makes much progress, which is kind of boring. And the other thing is you have to wait a while for it to really freeze properly, but it's pretty, anyway, it's a pretty hard banana. But more fun is racquetballs. Fortunately I got two. Fumble fingers. Okay, so heat, again, is flowing from the hottest thing to the coldest thing until they will be in what's known as thermal equilibrium. It's a new kind of equilibrium. We've talked about equilibrium where you're zero net force. Thermal equilibrium is when there's zero net heat transfer between objects. They are actually at the same temperature and therefore do not exchange heat. So I am bringing these two into thermal equilibrium. So it's a normal bouncy, lovely bouncy racquetball, or used to be. Ready? Yeah, we can do better than that. That's boring. It just bounced. Try again, buddy. You got to whip it pretty fast. but it will shatter. And my goal here is not to hit people, of course, but also not to hit the screen, because there have been times when we have put pieces of broken ball into the screen. There we go. Yay! All right, we'll continue on Friday.